In this video, I will talk about logarithmic functions and their graphs. The objectives for this lesson is recognizing and evaluating logarithmic functions with base A, graphing logarithmic functions, recognizing, evaluating, and graphing natural logarithmic functions, and then using logarithmic functions to model and solve real-world problems. So here we define what a logarithmic function is. Previously, we talked about exponential functions of the form f of x equals a to the x. We know that exponential functions passes the horizontal line test, which means that it is a 1-to-1 function, because that test tells us that the function is 1-to-1, and therefore the function must have an inverse function. And that inverse function is what we call logarithmic function with a base a. So the textbook definition is right here in the box. For x positive, a positive, and a not 1, y equals log base a of x if and only if x equals a to the y. So then the function f of x equals log base a of x is called logarithmic function with base a. The important thing to recognize is that y equals log base a of x and x equals a to the y are actually equivalent equations. So they pretty much represent the same thing. And because there's this relationship between logs and exponentials, these things are equivalent. So examples of these are, here you have 2 equals log base 3 of 9. The reason why that is true is because we know that 9 is 3 squared. And similarly, because 5 to the third is 125, then we can say log base 5 of 125 must be equal to 3. So because of that inverse relationship, logs and exponents are very much related. So when evaluating logs, we're going to remember that a log is an exponent. So that means that log base a of x is the exponent to which a must be raised to obtain x. So for instance, when you're given log base 2 of 8 equals 3, you're going to try to think of 2 raised by what gives you 8. So you ask this question, because I'm starting with 2, because 2 is the base, and then because 8 is given for the log, you're going to ask the question, 2 raised by what gives you 8? And because the answer to that is 3, then 3 must be the result of that log. So 3 is actually the exponent. So anytime we have a log base of something, then that is actually an exponent for that base. So we know that this one and this one are equivalent equations because they represent the same thing. Here we have an example. Evaluate each log at the indicated value of x. So what I'm going to do is, there's multiple ways of doing this. You can use your graphing calculator using the log function, or you can use Desmos to evaluate these things. And for the purpose of this video, I'm going to do one and show you guys how I can evaluate part A. So to evaluate part A, we're trying to find when x is 32, and because f of x is log base 2 of x, we're going to evaluate f of 32, which would be something like log base 2 of 32. So this is not intuitive to compute. I mean, we can think of, we can ask the question, um, what exponent, so you can ask the question, what exponent does make 2 equal to 32? If you know the answer to this in your head, you can go ahead and say, well, 2 to the 5th is equal to 32. Like, you can go ahead and try to reason and say, well, then it must be 5. So then the result of this must be 5. So then the input of this function is that number 32. The output for this log function is 5. So another way you can compute that is you can use Desmos. So I'm going to demonstrate that to you guys very quick using the Desmos app. Here. Using the Desmos app, I'm going to show you how I can do it. So whenever you have the Desmos app on your screen or whatever, you're going to always have this kind of like a keyboard thing where you can click functions on the right side or like whatever side it shows on. And then you're going to click miscellaneous. And then there you're going to see log. There's one log and then there's log base A. You're going to use log base A because we're working with different bases. So the first thing you're going to input is the base. So like say for part A, we needed to find log base 2 of x, where x is 32. So that's why I'm going to put 2 for the base. So I'm going to type 2 there. And then the input for the log is 32. And then close the parentheses. And then you guys realize the answer we got is 5. That's exactly what we did on the example. So feel free to pause the video and then work out the rest and then compare your answers with the next slide. Okay, here are the answers. Please check your answers and make sure that you got them all correct. All right, next thing we're going to talk about is we need to know a couple of properties of logs, and there I list them all. So these directly come from the definition of the logs with base A. So the first one is log base A of 1 is always going to be 0. So the reasoning for that is because a 0 exponent will always produce 1. And that's how we know that is true. Log base A of A is always 1 because we know A raised by 1 is always going to give you A. So that's why that's the case. And then for part 3, log base A of A to the x equals x, and A raised by log A base A of x equals x. So this is kind of like a property where you can move things around, and this is because of the nature of logs. And then lastly, if log base A of x equals log base A of y, then x and y must be equal. And that's because the one-to-one property. You guys remember previous video when I was talking about exponents, I said something like a to the x, let me write it this way. If a to the x equals a to the y, then x must be equal to y. And because we know exponential functions are one-to-one, then if you get the same output, then you must have the same input. So x and y must be the same. So similar idea holds for the logs. If you get the same outputs, then the inputs must be the same thing. All right, next thing we're going to talk about is graphs of exponentials and logs. So what I want you to do, pause the video here for a sec, and then try to use Desmos or your graphing calculator to graph these functions. One is 2 to the x, and then the other one is log base 2 of x. Please graph these and see what you realize. Okay, so you must get something like the following, where I provided two things in this video. One, a table of values is always useful when thinking about graphs. So I just listed a couple of input values here. So these are my input values. And then the second column are when we evaluate them. So these are output values. So you guys realize these are computed for log 2 to the x, right? So, and then when you plot these points, you're gonna realize it's gonna look like this curve that is for exponential 2 to the x. But then whenever you graphed the log function, you're gonna realize it's gonna end up looking like this. And then you guys realize these two functions are symmetrical with respect to y to the x. So they are symmetrical with respect to y equals x. That's true because they are inverse functions. They are inverse functions. Okay, so we're going to keep in mind that their graphs are going to be symmetrical with respect to the y equals x, the line y equals x, because they're inverse functions. Okay, so there's just a little bit explanation here, nothing more than that. A couple of things we're going to talk about. I think I'm just going to move on to this slide. So here, I'm going to summarize the basic characteristics of logarithmic functions. So first of all, domain, right? So what input could be used? So you guys realize input for this function. So when you have f of x equals log base a of x, you guys realize my input is always that x right here in the parentheses. So then output is the whole thing, is the result of that evaluation for x. So then we're going to realize what x's can we input. So the answer for that is it could be any positive number. So meaning x must be always positive number. You can't put 0 in because that would be undefined. So x is going to be always bigger than 0. Range could be anything. You could get any value from negative infinity to positive infinity. Part of the reason is you guys realize this guy, the curve goes to the negative infinity, and here it just keeps growing. So any output could be possible for positive x's. You're gonna always realize this. Oh, I forgot, the x-intercept is always 1 comma 0. So when x is 1, you're always gonna get 0. This function is always increasing from left to right, always increasing. And then it's always 1 to 1. I told you guys before, this passes the horizontal line test and therefore has an inverse function, which would be an exponential function. So a couple more features here. Y-axis is the vertical asymptote. So go back to the graph. You guys realize this function is never going to touch the y-axis. So y-axis here is always going to be, let me use a little bit better coloring here. Y-axis is basically your vertical asymptote, because realize the curve is never going to touch the y-axis. And the function is always going to be continuous, so no breaks, no inconsistency. And then reflection of the graph, y equals a to the x about the line y equals x. What that means is that when you graph the line y equals x, let's do that here very quick. So it's going to look like this. And then you're going to realize that the exponential graph, something like this, where you have f of x, y equals a to the x. So the inverse function for the log is given by the purple. They're going to be symmetrical with respect to y equals x. All right, so that's going to be all for the graph, and you guys will be hopefully practicing how to graph that. And then next thing I'm going to talk about is the natural log function, which is going to be very similar, but the only difference is we're going to have a specific base. So we're going to have a base where the base, is going to be a specific number, which is e, and that's approximately 2.71. Like I told you in my previous videos, if we end up using the specific base, which is very commonly used in mathematics, the function is going to look like log base e of x, which we generally write as ln of x. This is just a mathematical term for it. Instead of writing log base e, we just write ln x. So these two things are basically the same thing. It represents the same thing. And we're going to call this function natural logarithmic function. One thing we need to remember is that because log y equals ln x has log base e of x, the inverse of this is going to be something like, if this is like y, then the inverse of this is going to be an exponential function, which is going to be the e to the y equals x. So you guys realize these two things are inversely related. This is what we call natural exponential function, and this is natural log. Here we have the graphs for these. You can clearly graph log or ln x or log base e of x, same thing, and realize that the graph looks like this one. A couple of important things is the x-intercept is 1, 0, same thing. Whenever you use e as an input, you're going to get this plot e, 1, because ln x, like I told you before, is same as log base e of x. So if you use e as an exponent, then you get log base e of e, which is going to result being 1. So that's why that point is e, 1. Couple of other things. You guys realize the inverse function, natural exponential, is given with this red curve I'm marking. Same thing when you input for the x, if you input 1, you're going to get e to the 1, which is e. So that's why output plotted right here is going to be 1, e, which is symmetrical about this line, as you can tell. And then because this function is exponential, it's going to have a y-axis instead of an x-axis, and these points, you guys realize, also symmetrical. All right, so that's all for that part. Now you can use your calculator to do some practice when evaluating natural logs. So what we're going to do is we're going to practice. So let's do part A together. So it's going to be something like f of x equals ln x. So I'm going to replace x with 2. So f of 2 equals ln 2. A couple of ways of thinking about this. So you guys realize because ln is basically log base e, it's going to be equivalent to log base e of 2. So similar thing. So we're going to call, so the way we compute ln2 is generally it's easy to just use a calculator or Desmos. We can go ahead and do Desmos right here. So I'm going to do ln, I'm going to click the ln function, and because I was just doing ln2, looks like it's 0.69. So we're going to say this thing is approximately 0.69. So it's that easy to compute. So please pause the video and go ahead and compute part B, C, and D for yourself and compare your answer on the next slide. Okay, so one thing to point out here is that when you try to input -1 for ln, you're going to get an error. So the reason why is that because we know that for logs base a of x, you guys realize by definition, x has to be positive number. So if you input a negative number, you're going to get an error because negative numbers are not defined, because the domain of this function is always from 0 to positive infinity. So possible x's has to be positive number. Similarly, I showed you before, the properties for natural logs are listed right there. So you have ln1 equals 0 because e to the 0 is 1. ln e is 1 because e raised by 1 is e. And then because of the inverse property, we have e to the x equals x and e to the ln x equals x. If two ln's are equal, then their input must be the same.